Hi, everybody, and welcome to this recorded interview with Megan Anderson, geophysicist from the Washington Geological Survey. Megan, thanks for being with us today. How's the weather in Olympia this afternoon?
It's kind of gray. We
Same,
had a nice
same.
sunrise though this
Oh,
morning. It
good.
was beautiful. Yeah,
Well, early December, we can't be too picky, I guess, at this point.
exactly.
Let's get right into it, Megan. I was just so excited to see this new paper that got into my hands. I don't know how many months it's been out, but Deep Structure of Siletzia in Puget Lowland. It is perfect for the things we've been thinking about with this Cascades A to Z series thus far. We're thinking about the basement, and you've got some new data, it sure looks like, involving the basement in Western Washington. What motivated this work with Siletzia and maybe older portions of the basement to the east?
That is a great question, and maybe it's an example of how when you're a scientist, you don't always know what's going to turn up from your studies. I started trying to study the Seattle Fault, which is an active fault running underneath parts of Seattle, Washington. And I was trying to understand what that fault looks like as it goes down into the crust deep underneath Seattle. And I was trying to model it using a type of data called aeromagnetic data.
Mhm.
And we can talk about what that is later, but
Sure.
I was trying to model it and I didn't understand what the crust was made of in different places. There was this, rock called part of Siletzia. It's called crescent basalt there. There's a rock called the Western Melange Belt, which is over in the Cascades, but it wasn't clear where the transition was between those two types of rocks because they're not at the surface and not even
Yeah.
close. And so I couldn't come up with an answer to what the Seattle fault looked like until I understood what's the major component of the crust made of? Like, what is it?
Yeah.
What's it made of? And how does it affect the data?
Well, that's perfect because I guess I caught wind of the Siletzia story and have been teaching about Siletzia for maybe 10 years now. Ray Wells and some of your co-authors have been very helpful with that. But all I've had to work with is the map pattern. And I've always wondered, what does that pattern, what does that boundary look like in the subsurface? Is it vertical, or God forbid, does that boundary between Siletzia to the west and Western Melange Belt to the east, is that an angled or slanting
Oh
contact that
no,
that like
God
heads
forbid.
right into the Cascades? And I say God forbid because I'm like wondering, I guess in the last episode, I was wondering, is it possible some of the Siletzia basement rock is influencing the Cascade volcanic arc somehow? But it looks
Right.
like from your paper, it is a pretty vertical boundary. Is that accurate to think of it as a vertical boundary between Siletzia and Western Melange?
Yeah, I guess it depends on what you call vertical.
Okay.
Does it go straight up and down like a vertical line? No. It
Okay.
actually does kind of have like a dip or a tilt into the crust one way or the other. And what's interesting is to the north of Seattle, it actually does slant into the crust towards the east. So,
Towards the east.
shallow, yeah, it kind of dips towards the east. And then, but south of there, kind of at the latitude of like Tacoma, it actually dips to the west.
To the west.
Yeah, but it's fully dipping not under the Cascades. Like that whole dip story is underneath the Puget Lowland, and it doesn't seem to extend further than like the latitude of Lake Washington.
I want to go further in that direction, but can we make it a definitive statement then? What I think I just heard you say, it from your geophysical data in the subsurface, it seems very unlikely to have any Siletzia basement at Goat Rock's volcano or even Spirit Lake Pluton. Is that pushing you too far?
Let's talk about in the crust because what I'm talking about is in the crust at depths of maybe between 2 and 20 kilometers.
Okay.
So that's what we call the upper crust.
Yep.
Now, it could be in the lower crust.
Okay.
My modeling doesn't resolve that.
I see.
Some other data may have a suggestion it could be in the lower crust underneath the Cascades.
Huh.
But my data suggests, at least in the upper part of the crust, no, its boundary is west of there. And actually, some data that I've worked on in the past for DNR geothermal projects suggests that, yeah, it's actually fully west of Spirit Lake Pluton as well.
Okay. How about one more just kind of verbal one between the two of us, and then I'm guessing you've got a few images to share with us, and we can play with those a little bit.
Yeah.
Um, we're not drilling down to the upper crust to get your results. So can you describe for us dum-dums who don't know anything about geophysics, a rudimentary little description of some of your equipment and how you're trying to get this, or how you are getting some of this information?
Yeah, let's focus specifically on the kind of data I used for that paper.
Good.
A lot of people might be familiar with seismic data as a way that we can image deep down into the crust or underneath what we can see on the surface. It's a
Yeah.
pretty familiar one to some people. The
Yeah.
data I'm using is less familiar to a lot of people. It's called magnetic data. And what it is you basically take an airplane and you put a magnetometer in it. That's the name of the instrument, and you fly it. It's at crop duster altitude. So it's like this little crop duster plane with this um, instrument fitted into it. And they just fly back and forth over the surface, back and forth, and put together a bunch of lines of data that you can stitch together into a map. And what the magnetometer is measuring is, very simply put, how the rocks just below the airplane are changing Earth's magnetic field.
Mm.
And so it's a measure of how magnetic are the rocks down below. And that magnetism, uh, you know, it doesn't care how deep the rocks are, it's going to be affected regardless. So, if there's trees on the surface covering the rocks, you can still see the magnetism. If
Hmm.
there's a blanket of glacial sediment over the surface, it means you can't see the rocks below. You can
Yeah.
still see their magnetic properties. And so it
Huh.
helps us kind of see underneath the surface where we don't have exposures or things are kind of buried a little more deeply and we can't see it.
And does the magnetic signature of Siletzia and Western Melange Belt contrast beautifully for you?
Yes. It's really a really good kind of separation here is that rocks that are basaltic, like Siletzia and at least, in the Puget Lowland Crescent
Yeah.
Formation, which makes up Siletzia, um, basaltic rocks are quite magnetic. It's very uncommon to get basalts that aren't. And Western Melange Belt is a metamorphic rock, but it's made up of like basically sandstones that have been like compressed and metamorphosed. And sandstone is just not very magnetic at all,
Hmm.
no
Hmm.
matter what you do. And so, there are very few examples where a sandstone would be magnetic. So it's a really nice magnetic contrast. It shows up really well.
Let's look, if you don't mind, then. That seems like a
Yeah.
nice lead in to seeing a couple of things because I was excited, even though I barely understood some of those images in your paper. It sure looked nice and clear to me, even though I wasn't quite sure the data. I could see that boundary and it got me pretty excited. So I'd say
Yeah.
share away, and we can go regionally in the Puget Lowland if you like, or eventually get us down to the South Cascades would be icing on the cake, I'd say.
Yeah, and I am really excited to show you this data because just before I jump to the other screen,
Yeah.
the data I worked with for the paper was flown in like 1995. So it's been around for a while.
Okay.
And just in the last year and a half, the US Geological Survey flew additional data right over the South Cascades.
Okay.
And so there's a whole bunch of new data in the area that you guys are looking at.
Sweet.
And I actually, it's so new that what I'm going to show you is I've only gotten part of the data added to my big regional grid, so I haven't even
Good.
finished adding it in. So I
Okay.
almost think like there's more we could look at later if
Nice.
you find this
Oh,
interesting. So yeah,
well,
so
I'm
let me
sure
share
we
my
will.
screen.
Thank you.
Yeah, awesome.
It's like perfect timing. I don't know if this was meant to be or not, but like it just fell right in our laps here, and I'm so thrilled that we can do this. Oh yeah, okay, here
I
we
mean, that's
go.
what happens when you make connections, right?
I guess so.
Yeah. Yeah, so this is just my ArcGIS project for all of Washington. This is just the place where I just play around with data and look at it and
Hmm.
try to find relationships and show people stuff. So this is just my working map.
Okay.
And so, when I was watching your episodes, I was like, well, where's Russell Ranch Melange? I've thought of the Western Melange a lot, but like Russell Ranch, I'm like, what is that? Where is it? And
Yeah.
so this is a 500,000 map of geologic map of Washington. So
Okay.
um, Mount Rainier. I don't know if you can
Yep.
see my little cursor. That's Mount Rainier there. You can see
Yep.
the waterways of the Puget Lowland. Um, and Goat Rocks is like down over here.
Hmm.
And the Western Melange Belt, which I'm really familiar with, mostly crops out at the surface up kind of on the edge of the northern Cascades here in the foothills, kind of north of Monroe and that area. So
Very good. Yep.
yeah, and I've in this map, I've actually selected it. So I don't know, can you see it's kind of blue outlined?
Oh, it is fuchsia or whatever. It's
Yeah,
neon.
it's a
Yeah, I love
fuchsia
it. I
neon.
love it.
Yeah.
Yeah.
Those are all the rocks of that same age. I've just selected them all.
Sweet.
And so, yeah, so that we can kind of see them against the background of the geophysical data so we can have a kind of you know, indication of where these different rocks are. And you
Very
can see
good.
that that fuchsia color, there's none of it over by Mount Rainier or, kind of along the edge of the southern part of the Puget Lowland. Yeah, like you've mentioned in your episodes, it's just not exposed
Very
anywhere.
right.
Yeah. So what I'm going to do here on my map is I'm going to pull up the transparent. So what I'm going to take is I'm going to take the colors in the map and I'm going to make them transparent. Zoop. And now the colors have disappeared, so we can see just the topography, but you can still see those fuchsia outlines.
Sweet.
Yeah. So now we've just got a marker for where those rocks are. So what I'm going to show you now is the aeromagnetic data for Washington. And this is a version of that magnetic data that's very similar to what I analyzed in the paper. It's a little different. We can talk about that if you're curious, but
Okay.
let me turn that on. There it
Oh boy.
comes.
Oh boy. Oh boy.
All right, seeing that now?
I am.
Okay. So let's just orient a little bit. You can still see the kind of fuchsia outlines there. There's Russell Ranch. Here's the Western Melange Belt.
Thank you.
And just for, your audience and for you, Nick, the red colors mean that the rocks below the airplane are really magnetic.
Uh-huh.
And the blue means it's not magnetic and getting into kind of like those dark purples, not magnetic at all.
Sure.
Uh-huh. And so the area that I analyzed for the paper is kind of up in this area up here. So that's
Okay.
Puget Lowland.
Yeah.
And I don't know if you noticed, but over on the left side, you see all these highs, these yellows and reds over here. There
Yep.
is a big purple section, which is interesting, but it's mostly like yellow and red over here. That's the crescent formation,
Mm-hmm.
and that's what's making up most of the crust. And what I was examining in my paper is once you kind of up in this area near Tacoma, as you go to the west, you get from these yellows into more of like these blues and purples.
Sure.
And so the modeling I did in my paper showed that this kind of boundary between the yellows and the blues is where the boundary of Siletzia is. And, you can see that here's Mount Rainier. You can, and, the different Cascades volcanoes would be over much further to the east than that
Sure.
boundary is.
Yeah.
Yeah.
And so you said 10 minutes ago that north of Seattle, that boundary dips a little bit to the east,
Hmm.
but not in a significant way to get Siletzia stuff underneath Glacier Peak volcano, for instance. There's no evidence of
Right.
that, at least in the upper crust.
At least in the upper crust, exactly.
Okay.
Yeah.
Okay.
So yeah, so I was looking at this data, kind of thinking about your questions for this series, and I'm going, all right, well, I've been thinking about this area down kind of near like Rife Lake and
Mhm.
Mount St. Helens for a while, and thinking about, well, you have this boundary here. Well, what happens when you go further south? And
Yeah.
you can see that this blue purpley color, it keeps going south. And as it goes south, it actually starts kind of trending to the east. You see it
Oh,
heading over this way? All of
yes.
this bluish purple zone, this big kind of swath of blue purple. Like, is that must be it continuing to the southeast because it's all kind of the same color, right? And I've also worked, do you see also that same kind of blue purple right in here?
Yes.
Yeah, that's near Rife Lake and the Mount St. Helens seismic zone.
No
So this
kidding.
is west of the Spirit Lake Pluton. And I've also done some modeling across this for some geothermal projects. And the modeling I've done down in here suggests that this piece of blue and purple property is also probably some sort of metamorphosed sedimentary rock. It's very appropriate for that kind of rock. Um, then the other thing you can see, do you see this kind of yellow color here? There's almost like a circle.
Yes.
Yeah, that's a Spirit Lake Pluton.
Oh, wow. Okay. Okay.
Yeah, that yellow
Okay.
blob there is the Spirit Lake Pluton. And the modeling I've done now down there suggests that when some of these plutons come up to the surface and enter into the volcanic rock, you get a little low pressure metamorphism of the
Hmm.
volcanic rocks that
Hmm.
makes a metamorphic rock we call hornfels.
Okay.
And that rock, when we've measured it at the surface, its magnetic properties is very, very, very magnetic. And so we think that that's probably all like Hornfels material up above the Spirit Lake Pluton, kind of in between where it comes to the surface. All the volcanic rocks in between have been like metamorphosed to make this magnetic rock.
Okay, Megan, I'm going to ask you momentarily, can you stop your
Yes.
share? And then I want to come right back to this, but I think I'm hearing a couple of things and you're going to have to pull the reins back on me, I guess, if I get a little too bold here. But why couldn't a bunch of that bluish, purplish stuff where you're confident it's Western Melange Belt north of I-90,
Hmm.
why couldn't that all be Western Melange Belt surrounding the Spirit Lake Pluton and going all the way over to the Rimrock Lake Inlier and even as far south as the Columbia River Gorge, where
Well,
nobody says there's Western Melange Belt, but they say it's possible it's in the subsurface. What are you?
yeah,
Yeah.
I think it's entirely plausible that a lot of that is Western Melange Belt that's been intruded
Huh.
by these plutons.
And
Um,
I'm just trying to think kind of in real time with you, like what other units would even be possible for that bluish thing? Like it would have to be sedimentary or not necessarily. Are there, I guess I'm pushing it too far now.
mhm.
You're seeing the blue continue, and that's I'm getting greedy. That's good enough. It's not like, and that does seem new to me. I don't know if is that kind of, are you saying it's kind of new to you as well to see that blue extend so far south?
Yeah, and I will put in a caveat.
Yeah,
The the properties, like those physical properties of magnetics and like, what it looks like to the geophysical measurements, that
yeah.
rock, you could also have a rock that's like a low magnetism, like not very magnetic, like granitic
Oh,
batholith could also do that. But everywhere we have those kinds of rocks that we've seen in Washington, they're they're actually showing a lot of magnetism and not they're not
Uh,
they've got some magnetism to them. But that
sure.
could be a possibility, and we shouldn't
Yeah.
forget that.
Okay. Thank you.
However,
That's, yeah.
in answer to your second question, yeah, this is brand new. I mean, I would say, Nick, that I got this data this summer, and especially the data around and south of Mount Rainier is really brand new. And
Mm,
so I didn't know that there was this big purple swath extending kind of on the edge of Mount Rainier into the south. And so I'm scratching my head about it right now and trying to understand
nice.
it. It's fascinating. So
Oh,
yeah. And I
well,
would
that,
say that, one of the things I noticed is that the area where the Russell Ranch launch is on the map is also kind of this deep purple blue color
hmm
in
hmm
the aeromagnetic, which suggests that again, another place where we have this melange. It's not very magnetic, and it would create this kind of image with the magnetic data. So it's pretty exciting. And
I think so.
I does it extend to the Columbia River Gorge? I haven't added in the data set that would show us that. So it's actually one of my projects in December. Wait, it's December. This month and next month
Yeah.
is to take the new data that's been flown, basically from Mount St. Helens to the south to the
hmm
gorge. There's a whole nother section of data, and I'm gonna stitch it in, add it into this overall data set, compute some new um, maps, and then see what else there is to see. Because yeah, there's this big hole where I don't know what it looks like once we get to the
Right.
south, and it's pretty cool.
Love it. Remind me before we go back to a few, I think you've got a few more things you want to share. Before we
Hmm.
go back to those, remind me how deep you're comfortable going here. Like what we just looked at was down to 20 kilometers. Was that the number?
Yeah, around 20 kilometers.
Okay.
The kind of data that I was showing you. You can
Yeah.
play some games with some mathematical games with the data to try to see a little deeper. But then I haven't sat down to look at that data yet, and I'm excited to think about that too. We still see similar things in data that you can kind of massage it to see a little bit deeper. But I haven't done that yet, so kind of waiting to think about that until I get this other data added.
Sure. Does anybody know anything about the lower crust in the Goat Rocks or the Spirit Lake Pluton area? Like, is that a total black hole below 20 kilometers? I'm not even sure how thick the crust is in the South Cascades before we get to the Moho, but is that just a total question mark, or are some people saying the deeper parts of Siletzia are extending and slanting into the Cascade Volcanic Arc at that depth?
There have been some seismic studies of this area using the EarthScope US array data.
Oh yeah.
So that's seismic data.
Okay.
That suggests there's something that's pretty dense and high velocity extending in the lower crust. Kind of, it's it looks a little obliterated by the Cascades because those warm volcanoes, like warmth just makes seismic waves go slow.
Oh
But to
yeah.
the east of there, like underneath Ellensburg where you are, there's some really high seismic velocity materials that have been imaged, and people are wondering what that is. And one idea is that maybe the very lower parts of Siletzia, so like in the lower crust, maybe Siletzia has actually gone out that far. But it'd have to be, yeah, pretty deep, like 30, 35 kilometers down.
Well, that solves something that's bothered me for a long time. I keep hearing that from a couple of friends who are geologists, and they say, beneath your campus at some depth, there's some Siletzia, and I'm like, you're kidding me.
Maybe.
But yeah, but that question, I think, even though it's quite deep, I think you've seen enough of the alphabet that we've been doing that the Goat Rocks project wants to be as thorough as possible for possible contributions to those magmas when this stuff is coming up through. And
Mhm.
even though we're deeper than 20 kilometers, I guess they might have some signatures of Siletzia. If, again, we're not sure, but if we're that
Mhm.
deep and it is some a hell of a lot of basalt that might be Siletzia aged, maybe they do need to be aware of that possibility, but that's probably as
Mhm.
far as we need to go with that.
Yeah.
Um, okay, well, you've already hit a home run here. I've got exactly what I want, but I would
Awesome.
love to take a few more minutes if you have the time to look at a couple more things that may or may not be related to what we're doing with this alphabet. I would just love to take advantage of this, Megan. So please, let's go back and look
Yeah.
at a couple more things.
Yeah, that sounds good. I pulled up a couple more things. I actually have that seismic data pulled up if you want to see the image.
Sweet.
All
Love it.
right. Let's see. All right, you see my screen again or the map again?
I do.
Okay. So I kind of have slid the map further south. So again, here's Mount Rainier. And do you see this big hole in the data here?
I sure do.
That's that southern section I hope to fill in.
Oh, nice.
Yeah, and so I'm really curious what this, big zone of purple and blue will do when we get down into this area. I'm not sure.
Yeah, yeah.
And also, you can see what I mean about this is the Russell Ranch
Mm-hmm.
formation. And you can see
Mm-hmm.
how it's in this blue and purple area here too.
Totally.
I think something that's interesting to me is the Spirit Lake Pluton are these yellows. And then we've also got that same color here, which is
Huh.
in the Goat Rocks area is just right on the edge of it right here.
Yeah,
And so I'm wondering if this is maybe an intrusion due to the Goat Rocks, what made Goat Rocks, I'm not sure. But
sure.
it certainly looks a lot more like the Spirit Lake Pluton in terms of its magnetism.
Mm-hmm.
Mhm. So I'm just going to pull up my screen and show you. Yeah, so here's an image from it's a paper by Gao in 2011 using the US array data to image what the crust looks like seismically.
Hmm.
And I'm not going to spend a lot of time on this, but there's on the left side here, this is uh, seismic wave speeds at a depth of around 35 kilometers. So again, that's the lower crust
Okay.
underneath the areas where, I've been looking. And
Yeah.
this these are the Cascade volcanoes, the triangles, and you
Okay.
can see underneath the Cascades, it's kind of got these red colors. So seismic wave speeds are slower. That makes sense underneath volcanoes because it's hotter, and that
Okay.
makes the wave speed slower. But this
Yeah.
is what Gao was looking at. Do you see this big blue blob over here?
Sure.
That's the thing that he was looking at, and the data says, well, gosh, it seems like there's some really fast material out here, and that could be basalt. And he threw out a couple different ideas about that in the paper, but one idea is it could be part of Siletzia, again in the lower crust underneath that area.
Going all the way
Um,
to Idaho? Like
yeah.
that? Oh, Jesus. Okay.
hmm
Wow.
The pink circle here, that's the area where the Columbia River basalts came up through and erupted out. That's the center of where the Columbia River basalts came out.
Yeah.
And so another idea is that, oh, well, maybe when the Columbia River basalts were erupted, that made the big blue blob. But underneath where they came out, it's red. So it doesn't seem to match. So yeah, that's an interesting data set.
Very good.
Yeah. And the other kind of data you might think about looking at is something called magnetotelluric data.
Mm-hmm.
And it has magnet in it, the name. But it's not the same data that I'm looking at with this like aeromagnetic data that I've been showing you. It's actually measuring how conductive the crust is to electricity.
Mm. Okay.
And there was a study done in 2018 by a couple of my colleagues as part of the IMUSH study, measuring electrical conductivities around the Spirit Lake Pluton. And over to the left-hand side, you can see this is uh, basically electrical conductivity. If it's more conductive to electricity, it shows in red. And if it's more resistant to electricity, it shows in blue.
Okay.
And I think this is just one of the most amazing images. Look at the Spirit Lake Pluton is this big blue blob here. And all
Right.
around the edge is this red zone. And the basic interpretation in this paper, and my colleague Paul is the one who was the first author. Hopefully Paul, I don't screw this up. Um, that red zone is an area where there's maybe more fluids flowing through the crust, but the
Aha.
the Spirit Lake Pluton seems to be deflecting the fluid around the edges. And the area that I've looked at is right where this MSZ, those letters are on the west side of the Spirit Lake Pluton. I guess he's calling the Spirit Lake batholith here.
Yeah.
But the red over underneath the MSZ is a zone where I think that the fluids are probably coming up through, one of the melanges that is right on the edge of the batholith. And there's earthquakes there, there's the conductive zone, and it's also pretty low magnetism compared to the batholith itself.
So
Yeah, so
I'm wondering, this we're saving kind of quaternary volcanism until this
hmm
spring.
yeah.
We're not doing this winter, but
hmm
is anybody saying that the quaternary volcanism has a pattern to go around that red and that the Spirit Lake Pluton is somehow deflecting even the magmas? I'm not sure if that's the fluids you're talking about.
The fluids I'm talking about is really water that's being
Okay.
imaged. But
Yeah.
certainly if the batholith is deflecting the water, it might also
Right.
deflect the magma.
Sure.
And you can see how Mount Adams is over here on one side and
Yeah.
Mount St. Helens is on the other. This GR here, that's
Yeah.
Goat Rocks.
Sure it is. Yeah.
And you can see how it's a little bit more what we call as resistive or low conductivity. Probably because it's older, it's not active, there's no active fluids flowing through the crust. But and certainly with the active volcanoes, there seems to be some sort of relationship maybe between this data and the volcanoes. Um, you might see if Paul Bedrosian, who was the first author on this paper,
Hmm.
or I worked with Jared Peacock. They're both at the USGS. They might be
Okay.
interested in chatting with you about this work because I think it's fascinating. They'd have a lot of good things to say.
That's a good tip. Yeah, those are
Yeah.
striking images. Holy cow.
Mm-hmm.
Yeah,
Yeah.
I mean, I'm getting more and more interested in that Spirit Lake Pluton, and I didn't know anything about the thing 6 months ago. So it just keeps popping up on its own, just kind of in other conversations. So it seems to be
Yeah.
a major thing in the South Cascades. Very cool.
Yeah.
Uh,
It's definitely I think an area where researchers are really actively working and have questions and
uh,
are seeking out new data sources and gathering new data. So
sure.
I am really excited you guys are looking into it too, because it's fun to talk about this stuff with people. Yeah.
It is. How about a couple closing comments about your life at the
hmm
Washington Geological Survey? I'm getting more and more interested in intersecting with different personalities and
hmm
specializations with that organization. Are you kind of out there by yourself with that organization? Are you the only geophysicist doing your work, or how is your work tied in with the overarching goals of the WGS?
That's a great question. I am certainly not the only geophysicist. There's actually four of us there. And a lot of what we do, and particularly my job, is using geophysics to help the geological mappers better map the geology. And so as you can imagine, in Western Washington especially, it's very hard to map the geology because there's so much vegetation covering the surface. It's hard to find the rocks.
Yeah.
And so I talk about geophysics as being this kind of data that can help us. If you're going on the surface as a geologic mapper, you're finding a patch of rocks here and a patch of rocks there and a patch of rocks there. And so they're creating like the quilt blocks, right?
Right.
And the geophysics is the thread that helps tie them all together, right? And you need both to really fully understand, what the geology is at any given place. But the geophysics really helps us stitch together the observations and create kind of this more of this tapestry. And so that's my main job.
Well, a great example is what we just started with. We've got this ugly Russell Ranch thing down by White Pass. It's an island. Then we've
Hmm.
got some similar stuff north of Mount Si, and here you
Hmm.
come in on your white horse, Megan, and you say, "Look, we got blue going all the way through." I mean, come on now. That's what I saw.
Sorry, it's not
Um,
gray. I should have chosen a different color ramp and made it gray to fit your basement. Oh
oh,
well.
love it, love it. Well, hey, please hold the line. I want to chat a little bit when I'm done with the recording. But for now,
Yeah.
let me say thank you so much for your time. I hope we can do this again sometime, Megan.
Yeah, it'd be great to talk again, especially when I get that other data stitched in there. I'll be like, Nick, check this out.
It's a deal.
Yeah.
Okay. Thank you. Bye bye.
Bye.